Hey my dear students, welcome back. In this video we are going to learn Claisen condensation reactions. Before watching this video, I recommend to watch this previous video about aldol condensation, because in this video we are going to tell some differences between the Claisen condensation and aldol condensation. Let's dive now to the Claisen condensation reactions. It occurs between two esters, in which one at least should contain alpha hydrogens in the presence of one equivalent of base, such as sodium hydroxide. A reversible carbonyl condensation reaction occurs to yield a beta-Ketoester. This is the general structure of beta-Ketoesters. We are going to cover the most typical scenario. The first one is Claisen condensation of an ester with itself, not intramolecularly, but two molecules that are identical condensate with each other. So it must contain alpha hydrogens, like in this case, and ET, for simplicity, we are abbreviating the ethyl group. So the first step, we are going to do annihilation to remove this hydrogen. This annulate is going to react with another molecule. This lone pair here is the donor and is going to attack this carbon here. And this P bonding here is going to move here. And what is going to happen? I move this part below to understand who is going to connect, because it's connecting this carbon with this carbon here. Right, so now the difference between the aldol condensation and Claisen condensation comes here, because at the aldol condensation, if you watch my previous video, you had a protonation at this stage, but here we do not have the protonation. This is an alkoxide intermediate and you're going to have the elimination of a toxic group. So this is going to move here and this is going to go away, right? Now what we have? Right, plus hydroxide minus. Now this hydroxide is going to remove this hydrogen because it's still acidic as an hydrogen. And as a final step, we use acidification to protonate again this carbon here, right? As a mechanism. So this is going to get a proton, this is going to move here. Now, in some cases, you're not asked to write all the mechanism like we did here, but to write straight the product. How you're going to do that? You have to keep in mind that one compound here is two identical ones, like the above case. So this carbon here is going to have connection with this carbon here, or this carbon here is going to have connection with this carbon here, but is the same thing. Let's assume like this carbon here is going to make connection with this carbon here. So how to write it straight? First, what do you have? This carbon here is going to be connected with this one here. So at the one that is going to be connected, that is the acceptor, this is going to move away the atoxic group. This is going to remain the same, intact. Only this is involved with this carbonyl group here. So here, what we have? So this carbon here that is involved to make this connection, you have the ester group. And now on the other part, you have one hydrogen, and on the other part you have the remaining. Did you get it? Somehow. Alpha, beta. Let's move to other cases because you are going to memorize it more easily. Okay, we are now at the second case, mixed Claisen condensation reaction with esters. They work only when one reactant does not contain alpha hydrogens, like for example ethyl benzoate, this one here, or ethyl formate or metanoate. Let's treat now the case. Let's take a compound that contains alpha hydrogens, and after that we are going to add to this compound a Claisen condensation with ethyl formate. So first stage was the formation of the enolate. Right? And now this carbon is going to attack this carbon here. This is the donor, this is the acceptor. And what would be the final product without writing all the mechanism? Now, this group should go away, etoxide. The one that is the acceptor is going to move away the etoxide group. So, it's going to be this ester remain intact. And what is going to be connected here? Just this group, and it is forming an aldehyde, and this is the final product. Here in this case you have the formation of an aldehyde, right? H3O plus, because it requires also acidification at the end. Okay, let's move further. Now let's illustrate this exercise. Now you have one compound that has alpha hydrogens and one compound that doesn't have. In this case, it's ethyl benzoate. So let's write straight the product. What is going to be the product? Now, the connection. Now, you're forced to do this connection to this one, because on this case, from here, you cannot do any connection. You do not have any donor of the lone pair. It is not possible to form enolate here, because you do not have alpha hydrogens. Okay, so this is going to be this is going to remain intact, the ester, and now this is going to be connected with this carbon here. This etoxide is going to go away, and what remains? Only a benzoic ring. Right? This is the final product. If you react with a keton, you can form beta-ketones or beta-ketoaldehydes. It is possible to do this reaction. So the first one, how is going to be? This is going to be the final product, and is a beta-keton, right? Here you have two ketones. This one is going to be removed because this was the donor and this was the acceptor, right? In case if you react with ethyl formate, you're going to have a beta-ketoaldehyde. What is going to be the final product? So the final product, because this is going to connect here, and you're going to have a beta-ketoaldehyde, because this etoxic group is going to go away. Let's move now to the third case, intramolecular Claisen condensation reaction of esters. The dikemine cyclization, common name, commonly known, works best with 1,6-D esters or 1,7-D esters. The same story as with aldol intramolecular condensation. Here, be careful, this has to be, if it's symmetrical, it's going to give only one product. If it has any substituent, it's going to get more than one product as a final product. So in this case, what is going to happen? Here you have alpha hydrogens, and here you have alpha hydrogens. The first stage, the formation of enolate, for example, if you're going to form enolate at this position here, this enolate here is going to attack this carbon here. And what is the number of the ring, membered ring? 1, 2, 3, 4, 5. So you form a 5-membered ring. And now what remains? This here is connected with this one here. So this ethoxy is going to move away. So what you're going to have? Let's assume that the connection was made here. And here you have the remaining ester, and here you have the formation of the keton, right? As simple. A cyclic beta-ketoester can be further alkylated and decarboxylated. Look alpha carbonyl substitution video at the minute 12.40 seconds. Okay. Now, if you do here an alpha carbonyl substitution, what you're going to have? Now, the substitution is going to happen at this position here, at alpha. So what you're going to have? So here you're going to have, right? And here you're going to have, if you treat that with heat and in acidification, usually hydrochloric acid, hot hydrochloric acid, you're going to have as a final product this product, right? Plus CO2 plus ethanol, right? Thank you so much for watching. If you like this video, give a thumbs up and look forward to see you in the next video that is related with the naming of the amines. Up until there, peace.